Hello, I'm Lou Massa from City University of New York. I'm here at Mount St. Vincent University in Halifax on the program called Conversation with a Scientist to Dr. Chérif Matta. We'll be speaking about the quantum theory of atoms and molecules and perhaps other topics. It's my pleasure today to speak with Dr. Chérif Matta, who's a professor here in chemistry and physics at Mount St. Vincent University. His research spans many disciplines, including particularly theoretical and computational chemistry, biophysics, and astrochemistry. Dr. Matta holds a Bachelor of Pharmaceutical Sciences from Alexandria University in Egypt, a PhD from McMaster University in Canada, and a habilitation to direct research from the Université de Lorraine in France. He's published about 200 research papers and 4 books. Professor Matta's contributions have been recognized with various awards, including the prestigious John Charles Polanyi Prize for Chemistry. Polanyi, the Nobel Prize winner in Canada. Also, the Molecular Graphics and Molecular Simulation Society's Silver Jubilee Prize. The Minister of Science of Poland Distinguished Visiting Professorship, the Mount St. Vincent University Research Excellence Award, and the Science Atlantic Speaker of the Year, to mention just a few. He is an elected fellow of the American Association for the Advancement of Science. He's a fellow of the African Academy of Science, a fellow of the Royal Society of Chemistry, and a fellow of the Institute of Physics, among other senior memberships in learned societies. Could we start our conversation, Chérif? Could you, for example, tell us a bit about yourself? I'm thinking, what could be your geographic and intellectual background and the roots of your work?
Thank you very much, Lou, for this kind introduction. And as you can tell from my Egyptian accent, I guess I'm from Egypt originally, where I grew up. I grew up in a family that valued learning and intellectual work. So I was lucky enough to be in a home full of books. My father had quite an extensive library at home. And because the family had a pharmacy that was prominent in Alexandria, Egypt, and it has been the family pharmacy for 3 generations, like since my grandfather, since the early 1930s. So there were really no other option for me but to study pharmacy, even though my interest since I was a child was basically physics and astronomy. So under family influence, I had to study pharmacy. There was no other option, basically, in Egypt at that time. And then later on in my career, I switched back to my early love of physics and astronomy. So I would like to show you something here, some slides. This is my father, Farid Matta, in his pharmacy in Alexandria this is in the 1980s.
Yes.
Mid 1980s, I would say. The pharmacy was called in French, the label outside was in French. It was Pharmacie Matta, because the French is kind of the family's second language. It's the first foreign language. Of course, our native language is Arabic. But we speak French as frequently at home as we speak Arabic. So this is why it has this French name, and that's my father there in a very day-to-day situation in the pharmacy. And I trained in this pharmacy, and I worked there in the summer during the summer break from the studies from the Faculty of Pharmacy of Alexandria University. And during that time, even before that, when I was a teenager, because of my strong interest, I mean, when I was even in elementary and high school, I picked up a very strong interest in astronomy. And I built a telescope from scratch. The telescope that you're seeing here, where one of my nieces now is using for fun to look through the balcony of our apartment in Alexandria. I built this completely from scratch. I ordered the lenses, I made the calculations, the focal lenses, the focal distances and so forth. I painted it in black inside, and I bought the wood and made everything.
Yeah.
And it's still there in Alexandria. As you can see, my niece here, like a few years ago, is just playing with it, basically. Yes. So I was also fortunate to have been educated at Collège Saint-Marc d'Alexandrie, which is a French French first language school. So, and what you can see here,
great building.
It's beautiful architecture. It has a fantastic church inside, and it's a really, really architectural, masterpiece of sorts. It has been built during the King Fuad time of Egypt, in the 1920s. Mm-hmm. But it's constantly renovated and it's kept in a very good shape. And you can see that there is a dome on the top, and there is a dome on the top of the dome at the very top of the building there. And that dome is metallic. This is an actual observatory, astronomical observatory that used to house a telescope, but not anymore. But when we were students, we used the roof. You can see the roof upstairs here to put the telescope. And I was shown the moon as maybe a 12-year-old kid or 13-year-old kid. And it just blew my mind when I saw the moon for the first time through a telescope. And that's where, that's how it shaped my interest in physics and astronomy. If I move on to the next, these are my mentors once I graduated from during my undergraduate years and early graduate education in Egypt. I started a master's there and so on. So these are my most influential mentors, scientific parents, if you like. Uh-huh. The late Professor Abdelaziz Saleh of the Faculty of Pharmacy, and later on he was a very senior member of the World Health Organization Eastern Mediterranean Regional Office in Alexandria, but it's the office that manages the entire region of the Eastern, one of the 6 main offices of the WHO. His wife, Professor Labiba El-Khordagi of the Faculty of Pharmacy, and Professor Muhammad Al-Rai, who taught me physics in the introductory year for pharmacy, but we kept in touch until now. So these were very influential people, and they all encouraged me a lot in pursuing an academic career, and this is one of the reasons I'm here now.
Yes.
And of course, once I moved to Canada, I immigrated to Canada, then Professor Richard Bader has had the most influence on me because he was my PhD advisor, where I spent like 6 years in my PhD because I asked him permission to take more physics and mathematics course than required. Of course, the field of the PhD was quantum chemistry, but I wanted to deepen my knowledge of pure quantum physics. So I went to the physics department and I took courses, I think like 6 more courses than required for the PhD. This is why it took me 6 years rather than 5, because I had 1 more year of courses that I was just learning pure mathematics.
Didn't Bader have a sign on his door that if it's not physics, he doesn't want to speak about it?
Yes, if it's not derivable from physics or not measurable, I don't want to discuss it. Don't waste my time. Exactly. You knew Bader, you were friends, and he admired you very much, and I think the admiration is reciprocal. So, and then by happenstance, I had the great fortune of working with the extremely high-placed scientist and intellectual John Charles Polanyi, who is the Nobel laureate in 1986 and a great intellectual. He is a great peace advocate in the world, especially in the field of nuclear disarmament. Forget the science for a moment. He has written something like 300 newspaper articles against the proliferation of nuclear weapons, and he has edited books on the subject and so forth. So he's, beside the science, he has also another parallel career that is equally impressive. Yeah. And he has won the Sakharov Prize, Andrei Sakharov, for peace and so on. So, And then I joined the group of distinguished Canadian scientists and bio-theoretical chemist, Professor Russell Boyd at Dalhousie University, and I did a second postdoc. I should have said Professor Polanyi was my postdoctoral supervisor at the University of Toronto, where I spent 2 years and a half. And then I spent another 2 years and a half under Professor Russell Boyd at Dalhousie University here in Halifax. Then during the years that were after the postdoctoral work and between that, after I became a professor, I was invited several times to be a visiting professor at Université Henri Poincaré, which were renamed later due to a merger with other universities in France as the Université de Lorraine under the leadership of the Professor Claude Leconte, one of the world's most distinguished crystallographers.
Yes.
So I did under Claude Leconte what is called the HDR, or the Habilitation de diriger des recherches, which is the equivalent of a higher doctorate in Britain, like the DSc, the Doctorate of Science, or the habilitation in Germany. And of course, yourself, Lou, is one of my constant mentor and always a source of inspiration for all sorts of things, and longtime friend and longtime collaborator.
Thank you, Chérif.
Thank you. I go back to my home. This is a discussion, right? It's just chat. So I'm flipping back and forth. So we're going back here to actually our home, my family home in Alexandria.
Yes.
My parents had an extensive library, as I said, and the most influential book in my life was this book that you see here in the video, but I will show it to the camera as well because it's just...
What's the translation of Le
Le Ciel, the Sky.
Okay.
It's in French. It's by Baron Alphonse Berger, who is a noted French astronomer, but not only astronomer, he's like
an intellectual.
An intellectual and a publicist of science. Like he was noted for, like there is an equivalent book on air, for example, that has the same sort of cover. And there are several books of him about bringing the science to the general public, a little bit like your interest and mine.
Yeah.
And so this book, Le Ciel, is a tremendously impressive book. I've never been impressed in my life by a book, and I have seen a lot of books in my life, but this is one of a kind in terms of the quality of the illustrations, the explanation, the beauty of the examples, and the sheer beauty of the printing.
Yeah.
But then there was one thing that I'd like to show the audience today that is truly extraordinary. There is a chapter in this book, and I have to use my glasses here. There is a chapter 13. It's called La vie sur les mondes, life on worlds, other worlds. So life on Mars, and there is a picture of Mars here. And then the author asked the question, are planets inhabitable? And if you flip a few pages, he started to talk about Martians, travel to Mars. And this book, notice that it has been published in 1923, where people have not yet been traveling with planes very much. It was just beginning.
100 years ago.
102 years, a century and 2 years, yeah. So the people were traveling by boat, like your parents came by boat to America, right?
Correct.
From Italy.
Correct.
So the book is extraordinary. So there is this chapter about the possibilities of space travel, including a trip to the moon and a trip to Mars. So the moon travel is truly extraordinary. If I can show this to the camera, because it's just unbelievable what the author has predicted and what actually has happened in the NASA travel 45 years later. This is, first of all, this table here that I'm trying to show here, this little table. Of course, the audience can look it up, the book, or can get a copy. It has an estimate of the time it would take for a rocket to leave Earth, 1923, beginning first quarter of the 20th century. it gives estimates of the several phases of the moon trip, and it sums up the phases to get an estimate of the total time for the space travel to the moon. And it gets you 48 hours and 58 minutes. The actual travel is 3 days.
Yeah.
Not bad. Not bad.
Pretty remarkable given the
Next.
time.
Yeah, next. So, and then he gives similar tables for Mars and Venus. And Mars, he estimates like it's 90 days. I don't know if, I haven't tracked the space that went to Mars or something, I don't know, but we can check it. Here is a picture of the Earth seen from the moon, according to an artist rendition, juxtaposed with the moon seen from the Earth. The fantastic thing that I find is that if you see the next slide, this is the picture I was just showing you physically. Yeah. The next page, so this is 23. I managed to crop an image from the NASA voyage of 1968 Apollo mission. I just managed to put it exactly in the same dimension and proportion as the left picture. And here's the juxtaposition. Look at this.
Wow.
1923, an artist imagination. 1968, an actual photograph. Right?
Beautiful.
Not bad.
Yeah.
So another person that had a tremendous influence on me is my uncle, Rafiq Matta. He's probably not even aware of this, but he had an enormous influence on me. Rafiq Matta is a very talented person, not because he's my uncle, he's my paternal uncle. But he's tremendously talented in the sense that he has also a dual career, as all these brilliant people have. So he had a career as a senior engineer with the government of Quebec, of the province of Quebec, as a city planner. And he has contributed to building many of the landmarks of Montreal, for example. But on the other hand, he has a dual career, a shadow career, or now it's becoming almost like his primary career as a musician and as a conductor, as a composer, and as a specialist of Baroque music, especially Johann Sebastian Bach, including the little generic that we have at the beginning of this program, has been chosen based on his recommendation. So he's the musical director and founder of the Ensemble Telemann, which is a Baroque ensemble based in Montreal. And here's one of the picture, but you can either Google him or search YouTube for some really remarkable performances by this ensemble, and including jazz performances using Baroque instruments. So it's really, really interesting. So, and the reason he had such an influence on me is while I was a kid, I was playing with equations and mathematics. And I was bugging him all the time, Rafi, because he's an engineer and so on. So I was going to say, to present him these little musing of a kid. And he would send it by mail, by physical mail, to his colleagues in universities across the United States and Canada to evaluate my work. And of course, the work this is child's play. I mean, yeah, he discovers this but he's like 80 years late, sort of comments. So he was like, he had a tremendous influence. Like I'm an avid listener of jazz and also of classical music, but mainly of jazz because I've been influenced by him mainly. So next, the major influence in my recent academic work is, of course, Richard Bader. Bader, a very distinguished scientist and quantum chemist of the 20th century and early 21st century. He sadly passed away in 2012. And just before his passing, I was asked to edit a special issue by the American Chemical Society of its journal called the Journal of Physical Chemistry A, this one. And it turns out, I was told that his Bader Festschrift, it had something like more than 85 contributed articles in this issue. And according to the American Chemical Society, it turned out to be one of the thickest, or perhaps the thickest, issue of the journal since its founding about 100 years ago. And to the extent that when they physically printed it, they had to print it in
Small
they print
font.
two pages per page because otherwise it would be too thick. It's about 1,000-page thick
Yeah,
volume,
yeah,
issue,
yeah.
enormous. And before, there was the Canadian Journal of Chemistry in 1996 has issued an equally extremely thick volume celebrating Bader's work, a special issue of the Canadian Journal of Chemistry here in honoring this fantastic scientist. So to get back to the work on the the work of Bader, which basically was the work in which I have done my PhD. The theory that he invented or created is called the quantum theory of atoms in molecules.
QTAIM.
QTAIM. And the book here that you see on the slide is becoming like a classic of science. And it's an Oxford University book of 1990. It has been cited tens of thousands of times. It's a classic of chemistry. So
Very interesting.
thank you.
So this theory of Bader, look at the title, Atoms and Molecules. Can you say something? Well, first of all, we know what, roughly speaking, what an atom is. It has a nucleus. The nucleus binds electrons around it. What is the idea of an atom in a molecule?
Great question. Thank you. So the atom, as we all know, is a collection of electrons that are basically attracted to a nucleus that is positively charged, and the electrons are negatively charged, and they are attracted to each other. And the atom should have a spherical symmetry by something called the Curie principle that requires if the atom had only one electron or a closed shell, in other words, all the electrons are paired. The electrons have to be paired. To have a closed shell, all the electrons have to be paired. In this case, if you have complete closed shells and or single electron atom, you have a spherical atom for two different reasons. If you have one electron, then the potential of the nucleus is spherically symmetric, and by something called the Curie principle, then the effect has to reflect the symmetry of the cause, even though between brackets, because I'm using these very loosely, the cause and effect is there's no causality in quantum mechanics, but you cannot. The effect has to have a consistent symmetry, or you cannot have if an electric field, let's say, that is spherically symmetric and have a distribution of particles that is not spherically symmetric. Right. Let's say in the atom, the atom as a part.
Free space itself is isotropic. Every direction is the same.
Yeah.
So that a free atom within space has to reflect the isotropy of space. It has to be spherically symmetric.
Even when you have to have partial occupation of orbitals, and then there is something called the Unsold theorem that says that the sum of any complete set of spherical harmonics is a sphere. So,
right.
But in the molecule, that breaks down, because the molecule, by definition, the field is no longer the field, and the associated potential are no longer spherically symmetric.
Right. If you have a nucleus here and a nucleus there,
it's finished.
There's a line between the two of them, and it's not a sphere anymore.
Right.
Yeah.
So now, how do you define an atom in this situation?
Yeah,
I mean,
that's the question.
A hydrogen atom in a hydrogen molecule. A carbon in a carbon monoxide molecule, for example. Where does the carbon ends and when does the oxygen starts? Let's say. So that brings us to the theory of Bader. This is his main contribution here to science. He has many other contributions, but this is the main one. So up to this Bader theory, and I'm going back to the slides here, up to Bader's theory, chemists would draw chemical structure on paper based on chemical knowledge, chemical intuition, and chemical understanding of the reactivity and how the chemistry work in the test tube. And you assign usually the chemical structure on the basis of the sheer distances between the nuclei of the atoms that are involved in the bonding within the molecule. So for example, here I have a collection of atoms, and whether you determine their positions by X-ray diffraction or by sort of nuclear magnetic resonance experiment like NMR experiments, at the end of the day, you have a bunch of distance, a distance matrix, a distance 1 from 2, 1 from 3, 1 from... And then you determine what distances are smaller than the radius of the atom in vacuum, let's say. And if the sum is smaller, you put a stick between them, and then you determine, based on your knowledge of chemistry, the so-called multiplicity or the bond order. Like, is it a single bond? Is it a double bond? So basically from this dot picture, if I move to the next slide, you can determine a chemical structure. Now that was done until Bader came along late in the 1960, late 1960s or mid 1960s and on. But the theory took shape in the 70s and it really matured in the 80s and the 90s. So Bader draws on a theory of topology, and topology is a branch of mathematics that deals with connectivity of points, vertices, and edges. And the connectivity can change abruptly in certain, during a chemical reaction, for example. You have a so-called bond that breaks and bonds that make, and so the structure would change abruptly. And the abrupt change in structures have been captured in a theory, mathematical theory, by the famous mathematician René Thom, who is French, from the Institut des Hautes Études Scientifiques near Saclay, near Paris-Saclay. And René Thom is a Fields medalist, and of course, for the audience, for the general public here, the Fields medal is the equivalent of the Nobel Prize, because in mathematics there is no Nobel Prizes, but the Fields medal is the equivalent prestige in mathematics. So he's a Fields medalist in 1958 for developing the theory of structural stability and morphogenesis, how morphology change and is stable. And he has a very famous book that is translated in many languages, including English, of course, Stabilité structurelle et morphogénèse, which is shown here in the slide. And Bader and René Thom never, in fact, to my knowledge, interacted in reality, in life, but Bader drew a lot of concepts from the catastrophe theory in order to explain abrupt chemical changes and describe the stability and the chemical structure in terms of structural domains that are stable with respect to small changes in geometry.
Yeah.
Like you have still the same basic connectivity. Like, for example, to give a very mundane example of a topological map is the you're from New York. They use the subway all the time, right? So in the subway, when you have the map of the subway, you don't care about the distance between the different stations. You care about their connectivity.
Yeah.
It doesn't matter if the map is out of proportion, like if you stretch the map or distort it, or it's the connection that you don't care. Same with the chemical structure. I mean, to a certain extent, the chemical structure preserves the connectivity that we'll define in a second, up to a certain point where it breaks and it falls into another structure. So that's the stability that he's talking about. It's the stability within small geometrical changes until it changes the structure abruptly. So Bader based his theory on an quantum observable. And this is it's a technical term that means it's something that is in principle determinable by experiment, but not necessarily determinable directly by experiment. The word directly here is underscored. So here you see an electron, 3 representations of the electron density in the plane of methanol, methyl alcohol, which the chemical structure of which you see down. But upstairs, you can almost sense the structure like I superposed here a structure on the map, the density map on the left top drawing. Yeah. You can, of course, look at this like the military does, the topographical maps. You can look from a plane above, and then you will see the topographical map like the one below here on the left, where you see the contour lines. Each contour lines is a height, and just color coded here by atoms. Basically, the hydrogen is yellow, the carbon is green, the oxygen is red, and so on. And the lines that you see drawn down in the lower left corner are not drawn, they are calculated. The chemists draw them on the right. This is the chemical drawing, the one on the right, bottom right, the one in white, like C double bond O, OH, C, HH. This is drawn by hand based on chemical knowledge. The one on the left is not drawn, bottom left. The lines that you see here are found in the density. They're between every peak that you see at the center of the oxygen, let's say, and the center of the hydrogen, or the center of the oxygen and one of the carbons, or between the two let's say between the two carbons, because it's unique. You can see that there is a point in the middle that is between the two, and this is called the bond critical point, and there is a line linking them, which is a line of maximum electron density in space that maps on what chemists draw on the other drawing on the bottom right.
Yeah.
But the mapping is not always there. There are cases. I'll describe this in a moment. So here is a cut through an electron density map of a DNA base pair, like the genetic code, one of the two letters of 4 that transmit our genetic information from parents to children. And you have on the left the guanine and the right the cytosine. And the lines, again, you can faintly see the chemical structure here emerging from these lines, but they are not drawn again. They could be a little curved. These are not lines. These are
computed electron density contour lines.
Yes, but they can be observed if you have a crystal, let's say, of the material. So if we move if I start fade this, I'll fade. We'll fade I want you to see how the structure will emerge from this. You see, the structure emerges naturally, and I will superpose it in a moment on the actual chemical structure that the chemist would draw on paper.
Yep.
The mapping is quite impressive.
I see it.
And you can see that the atoms are delimited, like the nitrogen has this strange shape, the oxygen has a strange shape, the hydrogen looks like a vampire or something, like a stealth airplane or something. They have these strange shapes. This is what you find. And what Bader's contribution to fundamental science is that he extended molecular quantum mechanics. There's no meaning of talking about a fragment of a molecule unless you have certain well-defined boundary condition that was found by Bader, and in doing in following his lead, you can recover pretty much all the laws of quantum mechanics that apply for the full molecule to part of the system that is bounded by these so-called zero flux surfaces that give the shape of the atom.
So Bader wrote down a mathematical formula which allows you to envelop every atom within a molecule into its own base and shape.
Yeah, it's the
zero. And then the ideas related to the quantum mechanics of the full molecule, in some sense, projects onto the basin of that particular atom. The quantum mechanics applies to the atom in pretty much the same way that the same ideas apply to the full molecule. That's the idea.
You said it
Thus,
much better.
you have atoms within a molecule.
Yeah. You explained it a lot better than I did, I think. Thank you. Yeah.
Thanks,
exactly.
Chérif.
Thank you.
But that's the idea you're projecting, right?
Yes, exactly.
Yeah.
And this was, go ahead.
So Bader conceived of this notion of what becomes of the atom upon molecular bonding.
Exactly.
Okay.
He extended the molecular quantum mechanics to subdomains. He calls it proper open quantum subsystems.
Yeah.
Yeah.
So, for example, the theorem, the famous theorem that's called the virial theorem, which is a statement such as the total energy is equal to the negative of the kinetic energy. That would apply to the whole stable molecule. But Bader would show how it applies to one of the atoms
Exactly.
within the molecule.
In fact, this is how we calculate the energy. You apply the virial theorem where the kinetic energy is minus half of the potential energy, and so you don't need to calculate the very complicated potential energy terms. All what you need is to only calculate the kinetic energy, and because the energy is the sum of the potential and the kinetic, it becomes, as you said, it becomes the total energy becomes just minus the kinetic energy. So you can calculate it. It's much simpler to calculate than calculating the potential terms.
So once you have Bader's atom within a molecule, you can go to every point within that atomic basin and look at what is the kinetic energy at that point.
Density at that point.
And you look at the kinetic energy density at that point. And of course, if you sum
you integrate it.
The effect of all of the points within that basin, then you get the total kinetic energy for that atom as it exists within the molecule.
With a negative sign, it becomes the total energy.
Yeah.
So that's exactly how it is. So that's how.
So you've simplified the problem of calculating this complicated energy quantity into one where you calculate the more simple kinetic energy, and you know the relationship between the two, between the kinetic energy and the total energy.
Exactly.
Terrific.
Again, you're explaining it a lot better than I can.
No.
So
I'm just trying to bring out what you're saying for the audience. Yeah.
No, thank you very much. No,
yeah.
I appreciate that very much. So essentially, we can say that the topography is not really I don't know if it is a branch of mathematics. I mean, I spoke with mathematicians at the Institut des Hautes Études Scientifiques in France. They don't consider it as a branch of mathematics, really. Topography is more a branch of geographers' toolbox, where you can study the surfaces like they do in the army, for example, the topography of a landscape, where you get the heights and the troughs and the mountains and, the topography, the shape of the surface.
Yeah.
But when you study the shape of the surface, you can abstract from that connectivities between the saddle points between the mountains. Let's say you have a saddle point and there is a ridge between two mountains, and that's the bond path. And so you can abstract, you can get a topology, you can connectivity that resists small changes in structure, which is the middle square here. And then if you go to the bottom right square, then there is the chemical structure that was known from the chemistry, from the experiment, from the expected intuition, and so forth. Usually there is, in the grand majority of cases, a one-to-one mapping between the middle square and the bottom right square. But there are exceptions in both cases. Sometimes you find bond paths where people don't expect, and otherwise we don't find bond paths where people expect. And these are led to a lot of controversy in the literature, including harsh criticism of, and any theory is not immune to criticism, of course.
Is that controversy in any way related to the hydrogen-hydrogen bond that you and Bader discovered?
Exactly. And, I brought this model here to show the audience what we mean. This is a general phenomenon, but I will apply it to one particular molecule just to illustrate the example. I teach first-year chemistry, and so do you. We teach the first-year chemistry. Biphenyl is a molecule like this. It has two benzene rings attached at the junction carbon here, the ipso carbons. And in gas phase, when this is in a gas, this biphenyl is not planar. It's actually twisted with something like 46 degrees roughly. It's a balance between two effects, as we say it in first-year chemistry. One of the effects is considered to be the repulsion between these two hydrogens that are close in space. They're considered to be repelling each other here. You cannot have them too close to each other because they repel each other. That's the so-called steric repulsion idea. Now, we have done Bader partitioning of the atomic basins of biphenyl in both the planar geometry, optimized, and when it's optimized, by that we mean we minimize the energy with respect to all the little changes in the geometry. So there are no forces on the nuclei by definition, whether it is a stable structure or not. You can have a stable minimum like a trough, and a ball in the trough, or you can have an unstable. You have a mountain and you have a ball on the mountain. It can still be there stable. It doesn't fall, but if you push it, there is no restoring force.
Right.
So this is an unstable, but it's an optimized geometry, in the sense that if you don't kick it, it won't move. And there are no net forces. Yet, somehow we tell the students that these hydrogens repel each other, and these hydrogens repel each other. This is why the thing twists. And it doesn't complete the twist here because there are more, it negates the certain degree of the electron delocalization between the two rings, so it gets a compromise like 46 degrees or something. Now, what we found by doing the Bader analysis, computing the energy in the way you just described very eloquently, that the energy of these hydrogens, these four hydrogens in question, in the planar geometry are actually much more stable, i.e. they have a lower energy than the others.
Hydrogen.
Which is very counterintuitive. What we further found is that the energy of this state as opposed to the energy of this state, this one is higher not because these energies are higher, but rather because the energies of this carbon is increased because of the little stretching that happens. So the electrons of this one attract the nucleus of that one less, and the electrons of that one attract the nucleus of this one less. Not because of these repulsion. In fact, these are much happier here than in here.
Yeah.
Now, that led to a flurry of controversy in the literature, of course, because it negates a first-year chemistry textbook explanation. But we are
steric repulsion.
Yeah, but now it's kind of getting more and more accepted. The papers this paper that you brought here with you, that was on the cover of Chemistry European Journal, has been cited something like 900 800 times or something so forth, and a second follow-up has been also cited 200 300 times. So yeah. it entered certain textbooks now, our explanation. So here I show in the slides. Here is the bond path that relate this in these slides. Here you can see the bond paths relating the hydrogens, and you can see that these are the basins, the volume associated with the hydrogen, and you can see the hydrogen near the center, the top or the bottom, are fused, and in fact this is what people thought it was repulsive, which doesn't make any sense because there are no forces in repulsive. Mean force. Repulsive and attractive mean force.
Right.
Force is minus the gradient of an energy. Minus the gradient. Force is a vector and energy is a scalar. There are no forces in an optimized geometry, no net forces on anything, on any nucleus. So it's an optimized geometry. So there is an abuse of the language in the literature here that is kind of like sometimes almost irritating when they say they repel each other. There is no repulsion. You can say destabilize if you like. That's legitimate. But repel, there is no repulsion. It's an optimized geometry. So here is the situation where you have the rotation and at some point, poof, that bond path between these two snaps at certain rotation of the angle, and the bottom one is the stable minimum, So I want to conclude this by quoting Einstein. In yellow on the top is the actual quotation, but this quotation is simplified often by saying everything should be made as simple as possible but not simpler.
Yes.
And the HH bonding, in my opinion, in my humble opinion, is a case in point. It's a little bit more complicated than to say that these repel each other. They do not. In fact, it is these atoms are destabilized in the planar more than these are stabilized, overwhelming them, so that this is why it twists.
Yeah. It's a great discovery.
Yeah, thank you.
So we've discussed this controversy dealing with the fundamental cause for the equilibrium geometry of this famous molecule. What other controversies has the work been involved in?
Well, I will not call it controversy from now on, but I will call it, there is also, we scientists like precise language. We don't, we try to use as precise language as we can. Like, as I said here, in this case, we don't use the word attraction or repulsion. We can use the word stabilize or destabilize, but not repel or attract. That's not legitimate. There is another thing that I read a lot in the literature, especially the biology literature, the biochemistry literature, whereby they say things like this statement here, that hydrogen bonds cause the stability of proteins or stuff. There is a causality implied in the statement, and this is a very common occurrence in many textbooks and so on. But again, there is an issue with the language here, because it's a chicken and egg. It's like a chicken or an egg sort of fallacy, causa principi. It's nonsensical to talk about whether bonding is the cause of the stability or the stability is the cause of bonding. They occur simultaneously, and perhaps a way out is to say they are associated with one another. They don't cause. There is no causality there. And it's funny, there is a funny quote by Bertrand Russell here that I like to quote. The law of causality, I believe, Bertrand Russell, like much that passes muster among philosophers, is a relic of a bygone age, surviving, like the monarchy, only because it is erroneously supposed to do no harm. Bertrand Russell. I don't necessarily agree with every word in this statement, but I agree that the law of causality does not make sense very often when it is actually implied, and it's abused. In my opinion, is sort of an abuse of the language. So,
in this context of
yeah,
the molecular equilibrium and so on.
Exactly.
Yeah. Shall we turn attention to your books?
Sure. Yeah.
So you've published 4 books. Am I right?
Yeah.
This is one of them. This is your most recent book.
Yes. This is appeared in 2024.
It's all about the localization of electrons, the delocalization of electrons. Can you say just a word about this book and maybe the subject matter indicated in the title?
Yeah, this book uses indices that describe electron localization and delocalization within a molecule as a tool, as a molecular descriptor to predict practical properties and to try to understand some of the chemistry of the compounds in question. We use it as a predictive tool. So we arrange, basically a localization index is an index that counts the number of electrons that on average are localized within the volume associated with the atom. Again, the idea of the atoms in molecules
Getting back
of Bader.
to Bader's idea of what is an atom in a molecule.
Yeah, but the ideas can be extrapolated to other partitioning scheme, but I am subscribing to Bader because it's well-founded in physics. So you have the number of electrons that are on average localized within the basin, and you have the delocalization index that measures the number of electrons that are delocalized between this one and this one, 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 this one and this. So you have a matrix, and you can arrange these elements into a matrix form, and then you can extract from the matrix invariant, as done very routinely by mathematicians. And once you do that, you can use the matrix invariants that are extracted from the matrix representatives of the molecules to correlate with empirically measured properties of series of compounds to predict the activity of those compounds that are not included in the series. So that's basically, we use it in a predictive way. And since in a predictive and sometimes the prediction provide explanation. Like, for example, one of the co-author of the book, Ron Cook, has discovered the active principle of some of the active species of some corrosion inhibitor through this correlation type work. And of course, the details are in the book, and I will move to the next slide here. Here is my two co-author, like noted quantum chemist, Professor Paul Ayres from McMaster, and distinguished and industrial chemist, Dr. Ronald Cook, who used to work on TDA research in Colorado, but has now retired, and enjoying life and enjoying writing books and writing papers now more, So I have to mention also my joint student with Paul Ayres, who did our master's degree with us. He's now, I think, in the industry of programming as a computer programmer. Is Matsuma, a brilliant person that has programmed all the work on the basis of which this method has been developed. So I thank him here publicly. And one word before I close this brief description of the book here is that we're very aware that predicting is not explaining, as is the long argument of, again, René Thom, the same person who was a philosopher of science. I love this book, by the way. It's a long interview. It's a series of questions and answers between René Thom and the questioner. It's in French, so you have to read French, but I don't know if it has been translated to other languages. But prédire n'est pas expliquer means predicting is not explaining, which you and I agree, of course, about, I assume, right?
Right.
Predicting is not explaining. Correlation doesn't mean causation, right?
Right.
But in certain cases, predicting does help explaining things, as we mentioned in this book. So on that note, I'd move perhaps to the next book, which is with you, Quantum Crystallography, which is this one.
Here's the quantum crystallography book.
Yeah, this we published in 2003. You're the main driver of this work. There is an entire program that we just filmed an hour ago about quantum crystallography, where I interview you and I refer the audience to this interview in case they're interested. But in a nutshell here, what the book is about is imposing quantum mechanical requirements during the solution of the phase problem of crystallography in order to extract much more information from the experiment than traditionally allowed by the traditional X-ray diffraction method.
Yes.
So you can extract energies and things like this. Yeah. And this is.
So here is a 2-volume work.
This is volume 2. This is volume 1 here, actually. Yeah. So this is volume 2 of a 2-volume book, as you say. These two. It's about 1,000, pages.
Here's the volume 1. Yep.
It's about 1,000-page book, whereby there are like 35-ish chapters by a bunch of noted chemists, including Adayunath and Jerome Karl, both of whom won the Nobel Prize in chemistry,
right.
Both of them. And you in a chapter, you have a chapter with Jerome Karl, and you have a chapter with Adayunath in this book. So basically here is applying, in this book, the different authors are applying quantum chemical methods, and including electronic structure, molecular dynamics, and so on, to try to understand the electronic structural basis of biological activity. And the picture you have here on the cover is the one that I played in the movie before, which is part. I did this picture during my PhD.
Yeah. Could we look at this book?
Yeah, the last one here. This is the earliest book I published with Professor Russell Boyd. And this is, again, I forgot to say, the Quantum Biochemistry is an edited book. I didn't write the book. I wrote a few chapters, but not the whole book. This is also an edited book. Professor Russell Boyd and I edited this with a foreword by the very well-known quantum chemist Axel Becke of B3-Lip fame and of many other things in density functional theory. And it's a bunch of chapters that try to update the field of QTAIM, the quantum theory of atoms in molecules, to the time of the publication of this book.
Yeah.
So
Really great work, Chérif.
thank you.
Chérif, you have other interests. One of the ones that I'm interested in particular is this 100-year-old problem that's never been solved, although everybody works on it. It's the question of the diffuse interstellar bands and what is the chemical source of these diffuse interstellar bands. Can you just say a bit about this problem?
Yeah, I'll say it briefly because there is an entire episode of this series, A Conversation with a Scientist, whereby I interview Professor Tina Harriott and Ailish Sullivan on the topic. So the interested audience can go visit this episode. But here I'm going to say a couple of quick words. As you said, Lou, it's a century-old plus problem that there are, like, at least in the visible region, there are 560 almost lines, absorption lines of unknown origin. No one can know exactly the molecular carrier that actually give rise to these absorption bands.
So no matter where you look in the sky, you look at the light coming from various stars and spectra such as what you see on the board there, absorption spectra are measured. So there's something between the Earth and the stars that's doing the absorption. Nobody knows what the molecule is associated with that absorption.
Exactly. It's in interstellar medium that absorbs these lines, but we don't know exactly what chemicals are causing this absorption between us and these stars within our galaxy, mostly. So there is only one molecule that has very strong possibility, and this is C60 plus, the cation that you see here. There are only two lines that were related to the C60 plus, but other than that, all the rest of these lines here, indicated in white just for illustration purposes, remain unknown. And this is a very tough nut to crack because it's an inverse problem. I mean, we're working on it. I mean, you actually are the one that sparked our interest in this problem, and now I'm working with all. You will see the collaborator, but it's an extremely hard problem because, first of all, the chemical space is enormous. Like, the number of possible compounds that you can make within the boundaries of the chemical rules of the 118 elements of the periodic table is something to the 10 to the power 60. So it's 1 with 60, 1 with 60, in other words, 60 zeros, which is more than twice the estimated number of stars in the observable universe, in all the galaxies, etc. So it's literally an astronomical number of possibilities. Yet what you have is a fragment of a spectrum. You only have, we don't know if this is the full spectrum. We don't know if these lines is all what you have from this molecule, or they have other lines somewhere, in other parts of the spectrum. So you're looking at you're almost sure looking at a fragment of a spectrum, and you want to work your way back to get the originator. You're putting the cart behind the horse, so to speak. So, like this, picture here illustrate the point. I mean, if I have a cylinder and I project it on one wall, I get a square. But if I project it on another, I get a circle, and it is neither the circle nor the square. It is a square because you have partial information, and it is a circle because you have partial information, but in fact, it's a cylinder.
That's a good illustration.
So that's the situation we find ourselves in. So you have to start somewhere. So we are improvising in this field, and we are still learning. We're at a very early phase. We're like only 5 or 6 years in this project. So but as Mark Twain has said, the secret of getting ahead is getting started.
Yeah.
Or as Martin Luther King Jr. have said, you don't have to see the whole staircase. You just have to take the first step to advance. So at this point, I must mention the member of this team that I'm working with. Of course, you yourself have brought this to our attention. So, and you're still very actively involved in contributing in it. Professor Daniel Magis, who is a very noted astronomer, very, very talented. Professor Tina Harriot, a gravitational physicist of great knowledge and experience. Professor Cercis Moreira Boado, who is a noted quantum chemist, and Alice Surette, who is 1 week or 2 weeks away from defending her doctorate with Professor Moreira Boado. The pair, Fraser and Emily Smith, who are a sister-brother pair that worked with us. Ailish Sullivan, who did a lot of work as an undergrad with us, and also Elena Singh, who also did a lot of undergrad work while she was undergrad on this project.
Very interesting problem.
Yeah, thank you.
In this DIB group you're working with. Now, other topics of interest. Time is running short, but I know you're interested in the ATP synthase and the molecular biophysics problem related to that. Could you just say a word about that problem?
Sure. Yeah. Thank you, Lou. This topic came, and this is an example for the younger faculty members of where teaching and research overlap. I was teaching a course in a third year biochemistry course, and then it just hit me during the lecture that ATP synthase, which is the molecular machine that produces ATP, which is the molecule that fuel our body, our brain, our muscles, everything. It makes all the non-spontaneous reaction in the body spontaneous by coupling with them. So this ATP is fundamental for life. We can't live a second without ATP. We produce our own body weight of ATP per day. So we produce, and we consume it, of course. Otherwise, we would be balloons, right? So ATP synthase exists in an organelle in the cell called the mitochondrion, which is a double wall. It has two membranes, two phospholipid membranes, and it is inserted in the inner mitochondrial membrane.
Bag within a bag, sort of.
Bag within a bag. And that's where most of the so-called intermediary metabolism happens. The Krebs cycle and so forth happens inside the inner bag of the mitochondrion. And to cut a long story short, the moral of the story is that the Krebs cycle produces highly reduced cofactors that delivers their hydrogen equivalent to the inner mitochondrial membrane complexes. The hydrogen equivalent splits. The electrons continue through a chain called electron transport chain, while the protons are expelled against their will, so to speak, what we call concentration and electrical.
They go into the outer bag?
Between the two, the gap between. They're expelled against the concentration and electrical gradient, and they concentrate within the two membranes, the gap, the intermembrane space, and then they go through ATP synthase with the concentration gradient and the electrical gradient, and hence release the energy. And the energy is immediately captured through a rotatory mechanism in this molecular machine by forcing phosphate, inorganic phosphate, to combine with adenosine diphosphate to form adenosine triphosphate, which is shortened as ATP, that is then used to fuel the body operations. What we found is that beside the difference in beside the electric field due to the difference in concentration of protons across the inner mitochondrial membrane, we find that the protein itself, because of the charge decorating its surface, has in of itself an intrinsic electric field that adds or subtracts from the outer field. And that's new information because it can have, for example, if it turns out to be applicable in humans, it will perhaps lead to some modification of the way you calculate calories in food, for example. When you go to the supermarket, you have a number of calories. It may lead to that. I don't know. We're still looking at the human now because it's recent work. We're still working on it. But we found in bacteria and in certain mammals and in certain fungi that there is non-negligible contribution from the structure of the ATP synthase itself to that electric field and its associated electrostatic potential. Of course, they are related by gradient, minus gradient. And one of I'd like to mention who is involved in this work. I mean, Dr. Peyman Fahimi, who finished his PhD with me a year or two ago. Dr. Jean-Nicolas Vigneault, who did his work with Dr. Tang Nguyen Dang in Laval University. Islam Matta, who is a fantastic master student, who is working on, who is the lead author of the paper on the right here, on Chem Met Chem here, which is an article whereby he expands on the modification of ATP synthase in certain way to attack the bacterial and leave the human alone, so that as a way to treat things like tuberculosis or Hansen's disease, which is like commonly known as leprosy and things like that. It's a very, very interesting, it's an open access article, so anybody can access it. And Yuji Cheng, who did the fundamental work upon which this work is based. So, yeah.
Great work. So, you're from Egypt.
Yeah.
Originally. What's the language you spoke at home?
Arabic and French, both.
And nowadays, what are your languages?
Now I'm fluent in Arabic, French, Spanish, and English, and I'm really very interested in languages because I think they modify the way one thinks, even about scientific problem. Like if you read or philosophy, like if you read philosophy books, like unfortunately I don't know German, but I would have loved to learn German, but I don't. But because a lot of important philosophers are, of course, German. But if you read original books, like, for example, the Mario Bunge book on philosophy of science, I think it's called, I forgot the title of the book, but the treatment of the subject differ. It's not a matter of translation. The way the brain is formatted in different languages is different. And the way when you read, it's just like singing the songs, like you can recognize salsa, for example, or you can recognize a French song without understanding what they are saying. It's just the treatment, the musical treatment is different. There are different way of presenting the problem, not just translating the language, but just because of the structure of the way they are taught in the school. I don't know. I'm not a psychologist. I don't know.
Yeah.
But I find it, and I like to read at least in these four languages that I know, and I'm constantly trying to improve because, of course, they are far from perfect, very, very far. Like I have a lot of work to do on all of them. But you see the difference when you read something in the original language.
Yeah.
And I've been, been very fond of publishing in other languages. I published one paper in Spanish language, which was fun. I wrote it in for the.
What about giving seminars?
Yeah. I gave many seminars in Spanish in Chile, in Uruguay, in Argentina, in Mexico, in Spain. I've given a lot of seminars in French as well, and in Arabic, of course. Yeah.
So, Chérif, just before we close, is it possible for the benefit of the audience, we could indicate something about the program Conversation with a Scientist that you conduct here periodically at the university?
Sure, yeah. We patron this program, as I said earlier, on your program in City University of New York TV. And it's basically a conversation with a scientist or two. We haven't had three yet, but it's not impossible. And it varies according to their interest. It's not limited to any one particular area of science. It's general, and it's meant to the broad, educated public on YouTube and other electronic media. And here are a few snapshots.
Previous programs.
Previous on mathematics and arts, evolutionary biology. There is a program with you that is coming on quantum crystallography, on gravitation, on galaxies, and so forth.
Excellent.
Yeah.
Chérif, we're out of time. This has been fascinating, and in the English language, let me thank you for
Thank
being
you
here.
very much. Thank you, Lou.
Yeah,
It's
thank you.
good to have you here in Halifax.
It's so good to be here.
Yeah,
Thank you.
same here. Thank
Take
you.
care.
Thank you.